Swayam Prabha. Digital India. Educated India.
Hi friends, now we will discuss on the topic characterization of coal. In introductory module, we have discussed about the different properties of coal, and we have seen that some of the properties are very important to fix its price, and as we are interested to use coal as a energy source, so heating value is very important. And this heating value is dependent on carbon, hydrogen, oxygen present in it, and it also depends upon the ash content, moisture content, etc. So, in this class we will see what are the different methods that can be used to measure the properties of coal, like say what is the moisture content, what is the fixed carbon, what is the volatile matters content, and what is the carbon, hydrogen, nitrogen, sulfur, oxygen present in coal, and ultimately we will see how the heating value is determined. So, the contents of this class is the proximate analysis, ultimate analysis, and heating value determination. Now, we will see what is proximate analysis. This is a method, standard method, which gives us the procedure through which we can analyze the moisture content of coal, ash content of coal, volatile matter content, and fixed carbon. So, these four properties, moisture, volatile matter, ash, and fixed carbon. So, these properties are determined by proximate analysis. So, how it is possible? So, we have to take small amount of sample, we may take small amount of sample, and then we will heat it under certain condition that is prescribed in the method, that is 105 degree centigrade for 24 hours. So, then what is the mass loss? This is equivalent to moisture content, and after the loss of moisture, the dry material, if we put it in a crucible and cover it with the lid and then put it inside an furnace at high temperature for small period of time, then the volatile present in the coal sample goes off, and the difference between the initial mass and remaining mass will give us the measure of volatile matter present in the sample. In this case, the condition is given as 950 degree centigrade for 7 minutes in absence of oxygen, that is why we have given the lid on it. Then we will take this material and heat in presence of oxygen, so that the carbon, hydrogen present in it will be converted to CO2 and H2O. So, that carbon and hydrogen basically is from the volatile matters. So, during this process, in presence of oxygen, if we heat for a longer period at moderately lower temperature, maybe, that is, it is given as 750 degree centigrade and half an hour duration. So, that all this carbon and hydrogen will be converted to CO2 and H2O, and the remaining part which we will get, that is nothing but ash content. So, after that we can determine the fixed carbon by the difference, that is 100% minus the percentage of ash minus percentage of volatile matter and minus percentage of moisture. Now, we will see the volatiles, fixed carbon, ash and moisture content of some materials like peat, lignite, subbituminous, bituminous and anthracite. So, from this table if we see the volatile matters is decreasing gradually with the increase of rank, fixed carbon is increasing gradually, but for moisture and ash there is no such specific trend, because as you know that volatiles and fixed carbon, these are the inherent properties, these are present in the biomass, plant biomass, and it is converted to coal through coalification process. So, with the stage of maturity these two are changing, volatiles is reducing and fixed carbon is increasing as discussed in the introductory module. But moisture and ash, these two are not the inherent property every time. So, it also depends upon the external factors like say how we are handling the coal, how we are storing it, so all those things, and where from we are getting it, so all those factors, that is why there is no specific trend on it. Now, we will see how to determine the elemental composition of coal, that is called ultimate analysis. Sometimes it is also called CHNS analysis, C for carbon, H for hydrogen, N for nitrogen, S for sulfur. So, what is the mechanism for this analysis? What we do in this case, the coal sample is combusted at higher temperature. The specific temperature is given here, that is 990 degree centigrade temperature. When we heat it, then carbon is converted to CO2, H is converted to H2O, N is converted to NOx, S is converted to SOx. So, now we are getting a mixture of gas components. So, if we put the material in small container and then we apply oxygen and heat it here, then the gas will be available in this container. So, now we need one carrier gas. So, this carrier gas will carry the gas and it will mix it well, the components, and then we will use the methodology for the separation and identification of these gas molecules, which is possible by using a gas chromatography. But in this case we see we have carbon dioxide H2O, N2O, SO2. So, if I want to separate, we need the variation in the retention period of the different gas molecules in the GC column. That means, the interaction of these gas molecules with the stationary phase of GC column should be different. That is why NOx is reduced to nitrogen prior to its entry into the GC column. So, one silica tube packed with copper granules is used in the path of this gas. So, carrier gas along with the components passes through this and NOx is converted to nitrogen by reduction. Then the mixed gas is going through this separation stage in the GC and detection stage. So, you see here sample, carrier gas, combustion, then reduction for NOx reductions, and then mixing, then separation and detection. So, these are the different steps and mechanism for the analysis of carbon, hydrogen, nitrogen, oxygen and sulfur. Now, you see this figure is giving us different peaks, nitrogen, CO2, H2O and SO2, because we have discussed, because of the variation of the interaction of these gas molecules with the stationary phase of the GC column. So, retention period is different, as nitrogen is inert. So, its retention time is less, then carbon dioxide, then H2O, then SO2. So, these peaks area gives us the relative concentration of these different gas components. So, we calculate how much carbon, hydrogen, nitrogen, sulfur is present in the original sample. Now, we will see some example of the ultimate analysis of different types of material, including peat, lignite, subbituminous, bituminous and anthracite. Here also we see hydrogen content is decreasing gradually, oxygen content is decreasing gradually and carbon content is increasing gradually. But for nitrogen, sulfur, there is very less changes. So, 0.5 to 1.5. So, these small changes may be because of the limit of analysis of the instrument error limit, or here we see ash content also does not have any specific trend, because it also depends upon the external factors and the handling of the material. Now, we are coming to heating value. So, what is the heating value? So, that is most desirable parameter of the sample. We need higher heating value so that we can get more heat. So, if we take a sample, coal sample, and then if you combust it in presence of sufficient amount of oxygen, then it will release heat C plus O2 CO2, and if hydrogen is available H plus O2 H2O. So, these are the basic reactions which generates heat, and that heat we are interested to get in usable form. So, heating value is obviously the amount of heat energy released per unit amount of sample due to the combustion. Then here we can get two types of heating value, as we have discussed in the introductory module also. One is your higher heating value or gross heating value, and another is your lower heating value or net heating value. So, what these two are? So, after combustion we are getting flue gas, and during combustion heat is released. So, flue gas is having high temperature, it may be more than 600, 500 like this degree centigrade. So, that high temperature flue gas is used to produce steam from the water, and then the steam will be available in different temperature as per the need of the application in downstream. So, one possibility is that the steam is condensed, the which is used, which is the flue gas which is produced through the combustion, that is cooled down to atmospheric temperature. So, the heat recovered from this flue gas will be the maximum, that is called high heating value, and low heating value is the difference of the heat required to vaporize the water available in the flue gas. So, low heating value, higher heating value and lower heating value, the difference is we have to subtract the energy required to vaporize the water. Now, how this heating value can be expressed? What is the unit of it? So, unit may be kilojoule per kg, kilojoule per mole, or kilocalorie per kg, BTU per pound, and there are some conversion factors. Kilocalorie per kg to megajoule per kg, if we want to convert, this relationship we can use. So, people have tried to find out the relationship between high heating value and lower heating value, and it is found that HHV high heating value is equal to low heating value plus HV into number of H2O out by number of fuel. This number means number of moles of water produced during the combustion and number of moles of fuels. So, this divided by this NH2 out per mole of fuel, that will be the mole of water produced, and if we multiply it with the heat of vaporization of water. So, this amount of heat if we add with the lower heating value, then that will give us higher heating value. Now, let us see how can we determine it. For the determination of higher heating value, we use Bohm calorimeter, and Bohm calorimeter as shown in this figure. You see, this is the calorimeter, and inside this calorimeter we have water bucket, and then water bucket we put bomb, inside the bomb we put the material in this crucible and then fix it, and then we with the electric devices we ignite this one, the coal sample, and it combust inside it in presence of excess amount of oxygen. Then it releases heat during the combustion, and that heat is taken up by the water put in this water bucket as well as this bomb of the calorimeter. So, now what is the principle? The amount of heat released due to the combustion of the material inside the bomb is taken up by the bomb material as well as the water kept inside the water bucket. So, this is the principle for the determination of heating value in the bomb calorimeter. Now, what type of heating value this is? High heating value or low heating value? Obviously, it is high heating value. Why? Because inside this bomb we are putting the material and we are putting oxygen inside it in sufficient amount at higher pressure. So, we are assuming that complete combustion is taking place, and when the combustion will take place, the local heat will be very high, but that heat is being released, and this material, through this material or the bomb wall, the heat will also come to the water inside the water bucket, and there is some stirring arrangement. So, there will be some change in the water temperature. Now, if the sample is very small, so this variation in temperature may not be very high, it will be very within small range. So, what is happening? During combustion, moisture is formed and again it is cooled down to atmospheric temperature. So, that is why we are able to get complete heat released by the material, that is why it is high heating value. So, from bomb calorimeter we can determine high heating value. Now, I will explain the steps. So, what we will do? At first we will take 1 to 1.5 gram of material in the crucible, and then we will be using some thread or wire to ignite it, and after ignition we will be getting the temperature change, how the temperature is changing and what is the equilibrium temperature, what is the difference between equilibrium temperature and initial temperature. Then we will do the energy balance. So, how do we do the energy balance? We have heat released by this equal to, say, we have taken m amount of material. So, m into heating value of it, H is V, heating value of it, this amount of heat is released, and that is taken up by the calorimeter. So, that is equal to mass of calorimeter, say m, bomb mass m b into Cp or bomb mCp del T. This is the mass heat taken up by the bomb, and the heat taken up by the water, that is W into Cpw into del T. So, this is the total heat taken up by the system, and this is the total heat released by the material. So, if we ignore any other type of corrections, then this is the basic formula. Now, MBCP and this, from this relationship we can get MBCPB plus W into Cpw into del T. This whole term is replaced by W, that is water equivalent of the calorimeter, and this is the property of this material, what type of material it is taking, and in short the properties of the calorimeter. So, we are getting W into del T, this is the heat gain by the calorimeter bomb as well as the water body. So, this is the basic principle, and on basis of which we determine the HHV value excluding the correction factors. But here when we are using the coal and we are using some wire for the ignition, so then that will also release some amount of heat. So, that correction is required, and if the coal contains some sulfur and nitrogen, then that SO2 will be formed and then SO2 will be converted to H2SO4 or NO2 can be converted to HNO3. So, this acid conversion they will also contribute some amount of heat in this process. So, that has to be excluded to determine the HHV of this sample. So, now I will show you a video which is self explanatory, which explain us how the bomb calorimeter is used to determine the heating value of coal or any other solid sample. So, now you see the crucible part is getting ready. This wire connection is being made. Now, the sample is poured into the crucible. And the sample is put inside the bomb and it is fastened with the lid. Then we will put oxygen inside it. The bomb is connected with the oxygen supply line from the oxygen cylinder. Now, oxygen will go, it is started to go inside the bomb and pressure will increase, pressure is increased. So, this high pressure is basically needed to ensure that all the samples will be combusted. Now, the bomb will be put inside the bucket and water will be filled in the bucket. This video is made for demonstration purpose only. Yeah. So, the water has to fill so that the bomb will be completely immersed in the water, and then the electricity connection is provided. And the calorimeter is covered. The temperature measurement device is inserted and stirring arrangement is made. Now, we have to provide electricity inside it, and this is the device which provides electricity and also measures the differential temperature, the temperature difference. Now, we have to put auto 0. So, difference has to be made 0 first. Yes, now we see 0. Gradually we will reach the equilibrium point, the temperature difference will be fixed. You see here 0.683 degree centigrade, this is equilibrium temperature difference, the T1 minus T2, the initial and final temperature difference, we are getting 0.683, it is now constant, it will not change. So, that way we can get the del T value. Now, we are taking the we are recording the value. So, this is the video for demonstration for the measurement of heating value using Bohm calorimeter. So, from this video it is clear to us that after the process we will be having some parameters or some values like say temperature at the temperature at time of firing and final maximum temperature. See, in our case we do not have two different, but we have del. So, we are already getting the difference in the temperature during the process, and then C1 we get milliliter of standard alkali solution used in acid titration. So, what will be happening after the reaction, after the completion of this, we will release the oxygen from the bomb and we will take the sample out. There will be no sample theoretically, but in some cases some soutes may be available. So, in that case this run is discarded, not considered. So, then it is washed, the well is washed with water and that is titrated with alkali solution to get the acid deposited on the wall of it and how much acid is formed. So, that way we get how much, how many milliliters of alkali solution is required, that we can measure, and then we can get percentage of sulfur in the sample, that we should have some idea about the elemental analysis of the sample. And then what is the length of the wire which was fused during this process, that we have to determine. Initially we take 10 centimeter, then after this process how much is left, that we measure. So, the balance is used, we assume. So, that this value we get and mass of sample, how much sample we have taken, that also it is known to us now. So, on the basis of this information we can proceed further to determine the heating value of it. And as I discussed that without incorporation of any error, the energy balance formula we have discussed, but now there will be some error. So, heat of formation of nitric acid, heat of formation of sulfuric acid and heat of combustion of fused air. So, these three correction factors we have to consider, and this H2SO4, this is basically we measure from the presence of sulfur in the sample, and HNO3 heat how much can be released, that is measured on the basis of acid titration value, the titer value, how much milliliter of NaOH, KOH or N2SO4, N2CO3 is used. So, that basis, and heat of combustion of fused air also that is determined, and the supplier of this, manufacturer of this instrument, they provide the E3 value or corresponding how to calculate E3 value. So, how can we calculate E1, E2 and E3? So, E1 it is nothing but dependent on the C1 value. What is C1? That is the milliliter of alkali solution used to get the titer value of the wall wash of the bomb. And then E2 we can calculate by this formula 13.7 into C2 into M. So, C2 is the percentage concentration of sulfur in the sample and M is the amount of sample I have taken in gram, and E3 is measured through different equations for different types of fused wire used. So, nickel chromium if we use, then this formula 2.3 into C3. If we use iron 34B and S gauge iron, then 2.7 into C3, or if we use 34 gauge platinum wire, then it is equal to 0. So, these are provided by the manufacturer of the bomb calorimeter. Then how we will get the gross heating value? So, gross heating value into mass of the material, that will be the heat released, and that is equal to del T into W, that is equal to water equivalent into the temperature difference minus the amount of energy released due to the formation of nitric acid, that is E1, due to the formation of sulfuric acid E2, and due to the heat released by the combustion of the fused air. So, this is the formula through which we can calculate the gross heating value. Then this W value, that is the water equivalent value of the bomb calorimeter, that is the property of a calorimeter. So, we need to determine it. So, the same process is followed, but in this case we use a known sample, the heating value of the sample is known to us. So, one such example is benzoic acid. So, benzoic acid does not have any sulfur. So, C2 component will be 0. So, E2 will also be 0. So, in that case we will be getting W into T, that is equal to H into M plus E1 plus E3, E2 is 0. So, if we use this formula, so now H is known, heating value of the benzoic acid is known, how much benzoic acid we have taken, that is known, E1 we can calculate from the titer value, and E3 we can calculate on the basis of the length of wire fused wire used during the combustion in centimeter unit, and we can calculate the W value. Then this way we can calculate gross heating value or high heating value. Then how can calculate the net heating value? So, some formula is given, Hn net heating value is equal to 1.8 into Hg, that is high heating value or gross heating value, minus 91.23 into H, where H is the percentage of hydrogen. So, this formula is in this unit BTU per pound, but if we want to get it in kilocalorie per kg, we have to convert it, and this relationship we can use for the conversion of for the determination of net calorific value. Then people tried to find out some relationship of these two, high heating value and low heating value, with the amount of hydrogen, oxygen and moisture present in it. So, this is one empirical relationship which is provided. So, what we have come to know on the basis of this discussion, that to measure the heating value we need to perform experiment. So, it requires time and investment of manpower and money also. So, for general purpose, for the comparison of different types of coals, we may use some empirical relationship which have been reported by different researchers, as provided in this table. Different researchers, they have provided different empirical relationship for different types of coal, and some one are based on proximate analysis, some one are based on ultimate analysis basis. So, these will not be used to determine the actual calorific value of coal sample and to fix its price, but it will be useful, these will be useful to screen the coal samples when it is needed. If we have number of coal samples, we can screen it, that can be a suitable one by this applying this formula. Then I will give you some example. So, a coal sample with 1% sulfur is combusted in a bomb calorimeter. The temperature of the bucket water increases from 25 to 28 degrees centigrade. The water equivalent of the calorimeter is 2402 calorie per degree centigrade. 1 gram sample is used for the test and per 45 C10 wire is used for ignition. Out of the 10 centimeter wire, 2.6 centimeter is unused. To titrate the calorimeter washing, 24.2 ml of 0.0709 N sodium carbonate is required. This is equivalent to N by 10 NaOH. So, calculate the gross heating value of the waste, consider the thermometers are working perfectly. So, here there is no correction for thermocouple or thermometer is required. So, if we want to calculate the gross heating value, obviously we will use the formula just we have discussed. So, this is the formula Hg equal to T into W minus E1 minus E2 minus E3 by M. Now, we will see how can we get the value of E1, E2, E3 in this case, and what is the M, T and W value. So, here we have W value is given, M value is given, that is 1 gram, and temperature difference Ta and Tf it is also given. So, difference temperature we are getting. Now, T is 3 degree centigrade, W is equal to 2402 calorie per degree centigrade. E1, how can you calculate the value of E1? E1 is dependent of C1. So, C1 is given how much? It is given 24.2 ml. So, this will be E1 will be 24.2 calorie. Then what is E2? E2 depend on sulfur content. So, we have 1% sulfur. So, we will use the formula E2 13.7 into 1 into how much sample you have taken? 1 gram. So, 13.7 calorie is our E2 value, and E3 value is dependent on the wire which we have used, that 7.4 centimeter per 45 C10 wire. So, E3 will be 2.3 into 7.4 or 17.0 calorie. So, we have to subtract this with the TW. So, 3 is T into 2402 minus 24.2, that is equal to E1, and 13.7 E2 minus 17 E3. So, we are getting 7150 calorie per gram. So, this way we can measure the heating value. So, in this module we have discussed how to determine the approximate and ultimate analysis, how to determine the concentration of moisture, volatile matter, fixed carbon and S, and also how to measure the heating value of the coal sample. So, thank you very much for your patience.